Our time term inversion shows that we've got a two-layer case. The pink, which has got a velocity of 0.5 kilometers a second, and the blue, which is 1.7 kilometers a second. It's tempting to assume that everything you see on this inversion is correct, and the data here is as absolute as the data at this point, or at this point, or at this point. Now this is not necessarily the case, as we're going to show in a minute. But first of all, what we can do with Seismic is we can apply a modern processing technique called a tomographic inversion. And the tomographic inversion will display the data in a mode which is more true to real life, in that here, for example, it shows a very hard boundary between our 0.5 kilometer a second initial layer and our lower layer at 1.7 kilometers a second. This may be the case if the bedrock has been glaciated and very little weathering has taken place, but in areas of softer geology where there's no glaciation, it could well be that our bedrock has been heavily weathered, so in real life what you do have is, rather than having a very hard, sharp transition from one velocity to a second velocity, that you get a more gradual transition of velocities. And tomographic inversion, which we'll see in a minute, is able to take this much more into account. Now, again, what I'm doing here is I'm using the initial layered model which we created using our time term inversion as the initial starting point for the tomographic inversion. We can set some limits here as to the depths and our minimum and maximum velocities, etc., which the tomographic inversion is going to use. At the moment I'm just going to take the defaults which are presented to me here. We get a blocky model initially, and I'm going to smooth this by clicking on this button. So now that we can see, with the gradual change in colours from the pinks through the reds, yellows, greens through to the blue, that in reality what we have is not a very hard change in the velocity from the 0.5 kilometre a second topsoils down to our 1.7 kilometre a second bedrock. Instead we have, over the course of 1 or 2 metres, a much more gradual change in the velocity, which would indicate that the bedrock has been somewhat weathered. The next thing I'm going to do is ray trace this data set, and the ray tracing will show us which points in the subsurface have actually been sampled. Where the data has been sampled, it gives us a much greater degree of confidence in the accuracy of the data, but we will see that certain parts of this model have not been sampled very well, and all that is happening here is the computer is actually filling in the data in between. So I come here to ray tracing, execute. It gives us an RMS error here, and initially it shows us our travel time graphs and computed travel time graphs based on our model. If I come back here to displaying our velocity section and our ray tracing, now the computer program has drawn on our data set lots of lines, and the lines indicate where a seismic wavelet must have travelled from a shot point down into the earth, refracted, back to the surface to the geophone. Where the line is continuous, this is where our data has been sampled, but where there are gaps in the lines, for example here, the subsurface has not been sampled at all in this region, and all that has happened is the Seismic program has filled in the gaps and assumed that the velocity, which is 0.5 of a kilometre per second here, is also 0.5 of a kilometre per second here, and therefore it's the same in the middle. And you have to use your knowledge of geology and your experience to assume whether this is correct or not. Down at the bottom of our data set we can see all of this area down here as blue, but in fact the actual ray tracing shows that we've not really sampled the data set very much below where the green colours are. Only very seldom do the rays actually pass into the areas of blue. So when you make your interpretation of this, you can infer nothing about all of this area down below here. It shows it as one continuous velocity, but in reality you have not sampled it, so you cannot make any inference as to the velocities down here at the bottom of our data set. This screenshot shows our time distance graphs after we've performed the ray tracing routine. And now you'll notice that we've got, in addition to our travel time curves, we've got some theoretical travel time curves as well, which have been reverse calculated as a result of the ray tracing. Ideally speaking, the observed data, which is here shown in blue, should exactly match the calculated curves, which are here shown in black. And the difference between the two is shown as an RMS error. The better your seismic data is, the more accurate your first break picks have been, then the calculated curves will much more closely match the positions of your observed field data. The difference between the two is shown when the ray tracing is completed as an RMS error, and the rule of thumb is the smaller the RMS error, then the better your data. The processing steps that we've shown here in the two modules of Seisimager, PickWin for the first arrival picking and Plot Reefer for the inversion, form only a very small portion of what the Seisimager program is capable of, and we would always encourage the user to read the instruction manual, look at the tutorials, and have an experiment with the many other features which are available in this suite of programs. We thank you for watching these tutorials. We hope they have been informative. For further information, you can always contact us via our website www.geometrics.com. Thank you.